First of all, if you have any comments or questions, if I'm talking too fast, too loud, too slow, too whatever, just tell me. This is supposed to be useful for you and not so much for me. At some point, I will maybe not present so many facts, but more an opinion. And I would be very, very happy if we could start a discussion on this, because this is my opinion, and apparently I'm one of the few in the world having this opinion, and the others are all disagreeing. So for me, the question is, am I so incredibly smart and the others so stupid, or where is my mistake? And maybe you can help me finding the mistake so that I stop talking rubbish. So to start the presentation, the topic of this presentation is oxidoreductases, as Robert said. So enzymes that do redox reactions. And I hope that I will show you a few examples that these enzymes are actually super exciting for biocatalysis and for using these enzymes in organic chemistry. Simply because they very often do chemistry that you cannot so easily do with chemical catalysts. And I have a few examples on this, so we will go through this. But as the name says, oxidoreductases, so they catalyze redox reactions, and you all know that electrons are being transferred in redox reactions. So if a compound is oxidized, it gives away electrons. If it's reduced, then it takes up electrons. And it's always important to remember that if there is an oxidation reaction, there has to be a reduction reaction as well. Something is giving electrons, and these electrons cannot exist in space or so. They have to be accepted by another molecule. So if something is oxidized, something else is always reduced. And one of the big topics in oxidoreductases, of course, there is topics like how to find new enzymes, how to modulate the selectivity of these enzymes, how to make them stable under unnatural reaction conditions, and so on. So this is all research areas, and I think many of you will address these topics to some extent during your PhD projects. The project that the topic that I'm most interested in is how to get the electrons into the enzymes or to get the electrons out of the enzymes. And there I have actually two good news for you. On the one hand, this topic is boring because it has been solved. So 30 years ago, there were still a lot of articles written, the costly and not stable nicotinamide cofactor needs to be recycled. And unless we achieve something like 1,000 turnover numbers for the nicotinamide cofactor, we should not even think about talking about industrial applications. By now, we have a lot of regeneration systems available. There are many possibilities to regenerate these cofactors. So if you want to bring electrons into your enzyme with a cofactor, you just go into the literature, you choose 2, 3, 4 enzymes that have been reported for regeneration, and I'm sure that one of these systems will be applicable to you. On the other hand, the second good news is there is still a lot of things to do, because the systems that we are working with are efficient in a way that they will enable you to make the product in a small flask. But if you want to transfer this then in the end to an industrial application, there may be a few other challenges that you will have to meet. And these challenges are poorly understood yet, so there is still room for research. So you can apply these enzymes, you can apply regeneration systems, but there is still a lot of room for research to be done there, which of course should be the exciting thing for us as academics. Good. So, redox reactions for organic synthesis. So obviously we are talking about reduction reactions and we're talking about oxidation reactions. And I will start with the, let's say, simple case, the reduction reactions. And the reason why these are more the simpler reactions, the simpler enzymes, I will explain you actually in the second part when we are talking about oxidation reactions. So actually, third message of good news. This is a poor selection of enzymes and reactions that we can catalyze. There is many, many more enzymes and reactions out there, but those reactions that are established now, also on industrial scale, are keto reductions. So you take a carbonyl group, a CO double bond, and you can reduce this to an alcohol. You can do this stereoselectively. That's why enzymes are interesting for this. Or you can reduce them to amines. and you get pharmaceutically relevant chiral amines and compounds like this. So these enzymes and reactions are fairly well established now in the lab and on industrial scale. And a second class of reactions, the so-called ene reductases, NOED reductases that reduce conjugated CC double bonds, are coming up right now. So in the first part, I will be focusing on these enzymes. And then obviously, I will start now with the keto reductions. So the enzyme class that you use for reducing ketones or aldehydes to the corresponding alcohols is the so-called alcohol dehydrogenases. In the literature, you will find other names like keto reductases, K-REDs, many other names. These are all different names for the same class of enzymes. There is different groups that have different preferences for names. My preference is to call them alcohol dehydrogenases because the reaction is reversible, so you can also take an alcohol and take away a hydrogen from this alcohol and you dehydrogenize it, which in other words means you oxidize it. But the most interesting reactions actually is taking a prochiral ketone and reducing it enantioselectively to the alcohol, and then you get very nice products out of this. So where do the electrons come from? Obviously, this is a reduction reaction, and the electrons come from a molecule called NADH or NADPH. And yes, so what does NADPH look like? So this is the nicotinamide cofactor, and you will directly see it's relatively big. It contains a lot of different chemical bonds, a lot of chiral bonds. So making this natural cofactor via chemical synthesis is actually quite impossible. Now, of course, that's impossible, but that would be too difficult to synthesize. That's why we isolate these cofactors from yeast where they are present in relatively low concentrations. So NAD+, I think, in an exponentially growing cell is present in something like 1 millimolar or so, roughly. NADP is 10 times lower in concentration. So you can imagine that isolating these cofactors from whole cells is tedious and expensive, and that makes these cofactors expensive. And just to give you a number, these numbers change, but the latest number that I've calculated from the Sigma catalog was, I think it was 800,000 euros per kilogram of NADPH. So this is expensive. So if you want to do a reduction reaction and you put in 800,000 euros of NADH, your product really has to be very, very valuable. If it's only isopropanol that you make, then you are burning a lot of money, actually. So that was clear to researchers for a long time, and that's why we have been looking at the regeneration systems, which I will talk about in a second. Well, there is something interesting to talk about with this nicotinamide cofactor, because so this is the entire structure, and NADH and NADP only differ from the phosphate group at this oxygen, at this OH group. That is chemically a small difference, but for the enzymes it makes a huge difference. There are alcohol dehydrogenases that are absolutely specific for NAD, and they would never take any NADP, and the other way around. So this is important for nature to have different energy pathways for anabolism and metabolism, so to be able to dissect these two pathways. Well, the chemistry, the redox chemistry, actually only takes place at this part, at this nicotinamide moiety. And it looks like this. NADH, which actually contains two protons here, and one of these protons can be delivered as a hydride. A hydride to a carbonyl group, and you get a reduction reaction. So in principle, NADH or NADPH is some sort of organic sodium borohydride. It's an organic hydride donor, or NAD+ is an organic hydride acceptors. And the chemists amongst you will recognize that these molecules actually look quite similar to the Hansch esters. So the Hansch esters in organic chemistry are actually some sort of bio-inspired compounds. Well, there is another thing that is interesting to note is you can use this hydride donor and acceptor in both directions. So you can use NADH to reduce, and you can use NAD+ to oxidize compounds. And this is quite rare in chemistry. if you want to use sodium borohydride, you can only use sodium borohydride in the reduction reaction. But the corresponding salts of boron salts, you cannot use them for oxidation reactions. So chemical catalysts usually are good for, or chemical reagents are good for one direction. You can use chromium salts to oxidize alcohols, but you cannot use chromium salts to reduce alcohols. The nicotinamide cofactor can actually do both. And I think I will talk about this in a second when we talk about the mechanism. This is a highly simplified mechanism. So, not every step here has to be absolutely true, but basically it shows us what's happening in an alcohol dehydrogenase. Many alcohol dehydrogenases contain a zinc ion. It could also be an iron ion in the enzyme active site. And the function of this metal is actually only to coordinate and to activate. So in the first step, if we start with the mechanism here, the NAD+, let's start here. We are talking about reduction reactions. So NADH binds to this zinc or this iron, and the substrate binds to this iron at the same time. So the hydride donor is actually also already quite close to the substrate, to the carbonyl group. And then basically what happens is this system here is not aromatic. And you may remember that aromatic systems are usually very low in energy. So it's a thermodynamically favorable state for a molecule to have to be aromatic. So how can this nicotinamide cofactor become aromatic? Well, basically, if this lone pair goes into this bond, this lone pair double bond goes here, then this carbon atom must not have 5 substituents. So it basically throws out this hydride to the substrate, and you have this situation here. You get an aromatic nicotinamide ring, and at the same time, you have reduced the ketone or the aldehyde to the alcohol. So you have done a hydride transfer step, and this is energetically favorable because the nicotinamide ring becomes aromatic then. That gives it its energy. Well, it has a price to pay for this. And the price to pay is that all of it, now it has given away a hydride, so it needs to become a positively charged ion. If H- goes away, there must be a positive charge remaining. And formally, this positive charge now is located at the nitrogen atom. And you can imagine that nitrogen, being a quite electronegative element, does not want to have, wants to have more electrons and not less. So the price for becoming aromatic is that the nitrogen is getting into an electronically unfavorable situation where it's actually high in energy. And that is the reason why we can use the same cofactor also in the other direction. So we can use NAD+ to take away a hydride and get back to NADH. And this is feasible because then we satisfy the electron hunger of the nitrogen atom. So basically with the NAD cofactor, we have a very nice and very balanced redox system. So there is good arguments for using NADH for reduction reactions, but there is also good thermodynamic arguments for using NAD+ as an oxidative agent to take away hydrides. So it's quite balanced. You can use the cofactor for both reactions. That also means that the reaction actually is reversible, so that an alcohol dehydrogenase reaction is reversible, and you have actually the problem of how to shift a reversible equilibrium. We'll talk about this in a second. Well, and the rest of the reaction, so basically this side of the reaction is actually this side of the reaction, just mirrored. And the other parts are just binding of substrates and products going in and out. So that's not really important. What you should remember is NADH is a hydride donor and NAD+ is a hydride acceptor. Good. Any questions with respect to the mechanism? No, that's quite simple, huh? Okay, good. So, we have all these alcohol dehydrogenases, we have all these enzymes, you can make new enzymes, you can change the selectivity and everything. So what to do with them, especially considering that reduction chemistry is very old. This is a very established organic chemistry already. So where are the advantages of using an enzyme? Well, this is an example that I like very much. It is, you have this sulfur-containing heterocycle and a keto group. And for some reason, because, for example, you want to make this Zulu-pinene pharmaceutical ingredient, you want to do an enantioselective reduction. So what you need to know now is that sulfur and a CH2 group, so the CH2 group that is hidden here, they actually are very similar. The size is very similar. The electronegativity is very similar. So for a chemical catalyst, just swimming around in solution, the sulfur and the CH2 group really look almost the same, look quite identical. And if you want to do an enantioselective reduction, you want the reagent to attack only from one side and not from the other side at the same time. So if both sides look different, so for a catalyst, if it looks different to attack from here than to attack from here, then we get preferred attack from this side or the other one, and we get enantioselectivity. But if both sides are actually almost the same, then the probability of the chemical reductant to attack from this or the other side is actually the same. You get a racemic mixture. And this is a nice example coming from a company called Codexis. I think most of you have heard about them. They actually took a shitty alcohol dehydrogenase that accepted this compound, but at very poor reactivity, at very poor enantioselectivity. And then they did all their protein engineering, their directed evolution, and all the methods they have available. And after a few rounds, that's at least what they write in this article, they came up with the perfect catalyst. So you use one alcohol dehydrogenase to reduce this enantioselectively, and you can immediately use this compound to sell it to your customer. It's a reduction reaction, and this means we have NADH going to NAD+. It needs to be recycled in situ, and for this they have chosen a system called glucose dehydrogenase, which takes glucose and makes glucuronic acid or the gluconolactone from it. It's a nice irreversible reaction. It's just one of the regeneration systems. I think I will have a table on this. And the reason, you can now start building a story about green chemistry and everything around this, saying that with this product we save the world because this is environmentally so benign. And I would recommend you not to talk about green chemistry unless you prove it. So that is usually a nice argument, but if you talk about environmentally benign, somehow prove it in a way. But there is quite an obvious reason why this is advantageous, because it makes the company a whole shit of money. And why is that? Because the previous reaction, making this compound here, knowing that doing the enantioselective reduction is very difficult, if not impossible, so what they had to do was a chiral pool synthesis. So you start from an enantiomerically active, enantiomerically pure compound, an amino acid, and then you do 1, 2, 3, 4, 5 chemical steps, and you get to the same compound. 5 steps compared to only 1 step. And then I think the question which process is more efficient is answering itself. So while they fill one reactor here and make one reactor full of product, in the old process they had to fill the reactor once to get product 1, then refill it, get product 2, and so on and so forth. So they had to use the same reactor 5 times to get the same amount of product compared to only once with the new process. Of course, you can also mention that some of the reagents are actually quite dangerous and quite toxic. But I think the real reason for using the enzyme here is, you make more money because you fill your reactor and you get basically 5 times more product out of it, which means you get 5 times more profit from this. So that's a very nice example where a biocatalyst can actually do a reaction which chemically is impossible. So that's why I like it. And this is not the only example. This is just a list. The reference here should be the recent Nature article by Uwe Bornscheuer and some others, where they put a huge list of different products that are commercialized. And here I've more or less copy-pasted a couple of these products where these products are on the market and they are produced with alcohol dehydrogenase technology. So that's nice. So where's the issue? Well, the issue still is sort of the nicotinamide cofactor. You have to recycle it, and people have been aware of this issue. So in situ regeneration has been in focus of research for many years. And as a result, we have a lot of cofactor regeneration systems available. So you have seen the glucose dehydrogenase system, so GDH, which takes glucose as an electron donor, and then it oxidizes this carbon atom to the carbonyl group, which actually then is a lactone, and the lactone can actually hydrolyze, so you get a nice irreversible reaction from this. Very popular also is the so-called formate dehydrogenase system. So you take formic acid or one of its salts, you oxidize it. Basically, you oxidize this, that's the only carbon atom here. You transfer this one as a hydride to NAD+, and you get CO2 as a byproduct. CO2, in principle, can bubble out of the reaction, so you also have a very nice irreversible reaction here. In recent years, an enzyme called phosphate dehydrogenase has come up. So it oxidizes phosphate to phosphate. So in principle, you could use your buffer as an electron donor. So you start your reaction with sodium phosphate buffer instead of sodium or potassium phosphate buffer. And the buffer delivers the electrons, and it has a double function, keeping the pH and reducing your compound. So that's, yes?
Doesn't this change the pH of the reaction?
Slightly. So the pKa value of phosphate and phosphate are slightly different, but not really so much that you really need extra pH control. So this is quite interesting. I think one of the problems is here so we have been working a little bit with this enzyme, and it's actually prone to product inhibition. And if you have a buffer that inhibits your enzyme, then you might wonder if this is the perfect situation. But I'm sure that you can engineer new versions of phosphate dehydrogenase that are not prone to product inhibition, and then this is probably a very doable solution. There are other systems like electrochemical systems, using hydrogenases. Photochemistry will be coming up very soon on these systems. But they are more research related. And one driving force for research actually should be the amount of waste product being produced, or how efficient. So there are different ways to call a system efficient. You put everything into your reaction, you wait half an hour, and you get only product out of this. That's very efficient. But one question could be, how efficient is it with respect to using the electron donors? And one example, the glucose dehydrogenase is very efficient. It's a very fast system, but I believe it is very inefficient in utilization of its co-substrate. So glucose is a molecule that contains 6 carbon atoms. On average, these 6 carbon atoms have an oxidation state of 0. So in principle, glucose, if you see it as a battery, glucose could give you 6 times 4 electrons. So that 6 times 4, so 12? No. 6 times 4. You do the math. A lot of electrons. So in principle, glucose, 24, right? Yeah. That's why I'm a chemist. We count 1 too many. That's the mathematics chemists do. So in principle, you can get 24 electrons, 24 equivalents of NADH out of this. But this enzyme, glucose dehydrogenase, only oxidizes 1. So instead of using all of the electrons, you only use 2 out of these 24 electrons. And I believe this is a problem. I think this is an issue, not talking about pharmaceutical applications. Then we are talking about a few hundred tons per year of products. What's going on? Oh, cool. I wish I... Okay. Pharmaceutical applications, and most of the examples I've shown you are pharmaceutical applications. then we don't care. You know, a few hundred tons of glucose waste or gluconic acid waste is not an issue. And it actually does not really take food away from anyone. But if we envision going with these enzymes to bulk scale, so talking about 100 million tons per year, then 100 million tons of glucose being consumed, that is going to be a significant issue. You know, it is food being used for chemistry, and we're wasting the food for something, you know, not really useful. Of course, gluconolactone has some applications, but you know, you're not selling 100,000 tons of this product per year. No? So glucose dehydrogenase is very efficient because it's fast and it's nice and irreversible, but I think it has no future for large-scale applications because we will be using so much glucose, and that will be just an ethical issue. And it's not efficient because the battery, you know, it's like using a car battery to run your iPhone. That's not very efficient in terms of carrying things. So that is also one of the reasons why actually alcohol dehydrogenases themselves are very popular regeneration systems. So you remember the alcohol dehydrogenase catalyzed reduction reaction is reversible. So you could actually add another alcohol to this system and let the alcohol dehydrogenase oxidize this alcohol so it would regenerate its own nicotinamide cofactor. So instead of using two enzymes, the alcohol dehydrogenase to do your reaction and to use another regeneration enzyme, you just use one enzyme, the alcohol dehydrogenase, and you add another sacrificial electron donor, for example, isopropanol. And the chemists among you will recognize this reaction as the Meerwein-Ponndorf-Verley reduction. We just don't use a metal catalyst, we use an enzyme as a catalyst for this. So this is very popular, and there is actually good arguments for doing this, like using isopropanol as a substrate, because you can also use the isopropanol as a co-solvent, and if your starting material is not very water soluble, then using a co-solvent is a nice idea to get more of your substrate into the reactor, and for the company in the end to make more profit from one reactor. Well, it is, yes?
Is there some sort of preference from the alcohol dehydrogenase? Which alcohol is going to be oxidized?
No, it's statistical. Okay. So it's, you know, you have the alcohol dehydrogenase, and if the enzyme-bound nicotinamide cofactor is oxidized, then if a ketone binds, that will be an unproductive binding because the oxidized cofactor with the oxidized substrate, you know, no reaction. So then either the nicotinamide cofactor needs to get out or the substrate needs to get out. And then it's waiting for another pair of reagents. And if it's then NAD plus and an alcohol or NADH and a ketone, then reactions can occur. So basically it is a statistical process. Of course, the enzyme is enantioselective, so the desired reaction will occur enantioselectively, well, if you have the right enzyme. But you have the problem of a statistical reaction, a reversible reaction. So how do you shift the equilibrium? And the easiest way to shift the equilibrium is to put in more of one of the starting materials or to remove one of the side products. So here, acetone has a boiling point of 58 degrees or so. So just by heating up and reducing the pressure a little bit, you could actually remove the acetone and you shift the equilibrium to the desired side. Which not always works very nicely because many of the other reagents are also volatile. So by removing the acetone, stripping out the acetone, you also remove your starting materials or your products. So that can sometimes be very inefficient. And that's why a lot of people actually use a huge molar surplus of the co-substrate. So isopropanol is typically used in 20 to 100 times more than the starting material. So to shift the equilibrium, to have the isopropanol as a starting material, as a co-solvent, you use just much more of this, which is fine. It works. But again, we will have a waste issue because we will have the problem. You just need one equivalent of the alcohol to do the reaction. But the other 19 or 99 equivalents are just there to produce thermodynamic pressure to shift the equilibrium. But these are products that you are actually not interested in. So in the end, you will have to remove these compounds. You have to recycle them and everything. So this is actually not, from an environmental point of view, this is questionable. If it's really so good to apply, let's say, 20 times more of the isopropanol to shift the equilibrium. Now, this is just an equilibrium curve, which means that if you use a one-to-one mixture, then you are roughly at 50% conversion in the equilibrium. But for an industrial application, you need to have at least 95% conversion. And in order to achieve 95% conversion, you have to apply roughly 20 times the co-substrate in a molar surplus, which, from my point of view, is an issue with respect to the environment. And so I have to do a little bit of self-advertisement. Now, I will do more, but I will just one here. So one idea would be, why don't we come up with smart co-substrates? And the guys in Oviedo, they came up with smart co-substrates in the oxidative direction. So we thought, maybe we can find something in the reductive direction. And basically, the idea is you take a diol. You take a diol to be oxidized. And if you oxidize a diol, then you will get an an aldehyde alcohol, which can form a ring, a hemiacetal, which then can be oxidized once again to the corresponding lactone. So the idea of smart co-substrates is, instead of using 20 times more of the isopropanol, we use 0.5 equivalents of the smart co-substrate. Because the smart co-substrate is going to be oxidized twice, not once like isopropanol. And actually, the lactone byproduct is a dead-end product. It's an acid, so it's thermodynamically quite stable, and it's kinetically also irreversible for the back reaction. So we have two advantages. We make the reaction very irreversible, and we make it environmentally less harmful by producing less waste, which is really nice. And actually, Selinkara in Hamburg is now continuing this work. We stopped this work because, does any one of you recognize this molecule? Laura, you remember Alvaro. So gamma-butyrolactone. And that hydrolyzes to hydroxybutyric acid. And I still see no ring. No, this is the rape drug. That's what you put into drinks of women in a bar. If you don't have any other chance. So we stopped this project because we don't want to turn into a drug lab. Even though from a profit point of view, making a drug lab might be better than just having an academic position. But there is other opportunities. You can make other molecules, and then you're not talking about making drugs anymore. Good. So maybe I have 1.5 hours. Julie? Yeah. Okay. So maybe in 5 or 10 minutes we make a 5 minutes break, or just a short one for me. So there is so much more to talk about alcohol dehydrogenases, but I just wanted to give you a few ideas on what are the things that still can be done there. I would like to spend one slide, and that's not fair. It's really not fair because it's a very exciting class of enzymes, but I would like to take one slide on the so-called omega transaminases, also because they are typically not considered as redox enzymes. According to the EC classification, redox enzymes are EC1 and then .XXX. Transaminases are 3.4. Who's working with transaminases? Do you know the EC number of your enzymes? 2 points. So it is not a redox enzyme. But if you look at the reaction that these enzymes catalyze, so this is an example where this keto group is reductively aminated to the enantiomerically pure amine. Now, the chemist among you will say this is a reductive amination. So obviously, it is a redox reaction. And the byproduct, isopropylamine, is oxidized into acetone. Huh? Okay, I thought there was a comment. So these, to my mind, these are redox enzymes. Of course, the redox mechanism is not the typical mechanism like using NADPH or anything, but from my point of view, these are redox enzymes as well, which to some extent shows that the EC nomenclature not always is the perfect way to give enzymes a name. Well, what is worth mentioning here is you can make enantiomerically pure amines from prochiral ketones that can be very efficient. And actually, this example is quite famous, published in Science and Angewandte many times. And it actually also got the Presidential Green Chemistry Award some 5 years ago for substituting a wasteful chemical process with a better enzymatic process. Nice example. So it's definitely worth looking into these articles because they also show again a nice story about how far can you get with protein engineering and how can you solve a couple of issues from production by changing from a chemical catalyst to an enzyme catalyst. Very nice story to talk about. And that's my slide about transaminases. I think there will be more about, so you will hear more about transaminases. Yeah, and then shortly before the break, I want to start with the ene reductases, which is a nice model system with, for photocatalysis. I will not talk about too much about photocatalysis, but I would like to mention, Robert said, I think you said something like, I invented the photocatalysis also. When I was a postdoc in Manfred Rehd's lab, I was a desperate postdoc. I was wasted on a very difficult project, so I started doing other things. So we came up with the idea of light-driven regeneration of inuite reductases. And in those days, we were so convinced that this is a brilliant idea. Wonderful. Everything was beautiful. And we actually published this quite nicely. But we were convinced that we had invented this until we realized there is a paper from the 1950s. 1950s, where they had already published this idea. They used a different nomenclature, so that's why with the search terms that we were applying, we never found these articles. But in the 50s, people had already the idea. They didn't have the access to all the enzymes, so they couldn't do all these nice reactions, but they already had the idea. So know your literature. Try to dig back as far as possible, because the guys 50, 70 years ago, they were definitely not stupid. And they probably have already done quite a lot of the things that you want to do. So look at the old literature, try to modify your search terms so that you're sure that you get the old literature. Actually, I have a very, okay, that's leading too far. So, inuite reductases. Very interesting enzymes. Does any one of you know where the name old yellow enzyme comes from? Yeah? Oh, okay, so one. But the others don't know. Then I will spend a minute on this. So I think the first paper, that is a group by Warburg and another guy. And they were in the 1930s. They were looking at enzymes from yeast. And they found a yellow enzyme. And these, the cofactor of the inuite reductases is a flavin, so it's yellow. And they discovered in 1934 a yellow enzyme. They looked at the possibilities, what kind of reactions can you do, and they gave it basically no name until 2 years later they found another yellow enzyme, and in this case it was a flavin monooxygenase. So they had two yellow enzymes. So the first one was called the old yellow enzyme, and the second one was then called the new yellow enzyme. The new yellow enzyme now is called a Baeyer-Willinger monooxygenase, but the term old yellow enzyme has remained for a couple of reasons. And another funny story about these enzymes actually is, so they were discovered in the 30s. And then probably somewhere, I'm not sure when exactly, but in the 50s or so, there was a group in Munich. They were looking at very similar enzymes, but from Clostridia, Simon and the others. And these enzymes were actually quite sensitive to air. So what these guys then did, they published the work, and then they wrote, these enzymes are oxygen sensitive, so they are very difficult to use. And that was a typical example of copy-paste introductions. So, someone read this sentence, old yellow enzymes are difficult to use, so you should not use them. The next one was using that in the introduction, and from that on, it was copy-pasted until the early 2000s. So for 60 years, these enzymes were forgotten, completely forgotten. And then roughly around 2000, it was the group of Kurt Faber and actually Bernhard Hauer at BASF that looked at this article again, and they then realized maybe there is something, not wrong, but maybe it's too specialized statement. So they started looking for other old yellow enzymes. And basically now, within a few years, we realize old yellow enzymes are everywhere, and they are the opposite of fragile. They are stable in the presence of oxygen. They are very active. They are very robust. They are wonderful catalysts to be used in organic chemistry. So, these enzymes had been forgotten because I think the reason was because everyone thought these enzymes are not stable. And the potential of these enzymes has not been used for 30, 40, 60 years or so. And then two researchers come up, and they all opened up a completely new area of research. And now, since 10 years, we are seeing, basically every week, a new old yellow enzyme isolated from a funky microorganism that can do a few reactions. So this is really a booming area of research. So what do these enzymes do? So I will call them old yellow enzymes, but usually I also call them enoate reductases or en reductases. So I'm always talking about the same enzymes, but just different names are used nowadays. I think the best way is call them old yellow enzyme. It's also a nice name, I would say. So you have a conjugated CC double bond. So if the CC double bond is isolated, the enzymes will be inactive. But if the CC double bond is conjugated to a ketone, to a nitrile, to a nitro group, an aldehyde or whatever, then they can actually be reduced. And usually this reduction is performed stereoselectively. So with one reduction reaction, you can create up to 2 new chiral centers. Quite interesting, even a bit more versatile than the chemistry you can do with the alcohol dehydrogenases. And of course, simply because it's a reduction reaction, this NADH serves as an electron donor, and you need to do some regeneration of the NADH. And you can use glucose dehydrogenase, formate dehydrogenase, electrochemistry, hydrogenases, everything for doing these reactions. So nice. A few examples of, a few of them are actually already industrial processes where these enzymes are used. And I think BASF is the leading company with this enoate reductase technology. Well, I'm not so sure. So what do these enzymes do? So in this case, the nicotinamide cofactor is usually not the reductant, but it delivers electrons to a flavin cofactor. So there is an FMN, a flavin mononucleotide bound to the enzyme active site, usually not covalently, but usually very tightly. And this FMN is reduced by the nicotinamide cofactor, and basically you get FMNH2, the reduced form of the flavin cofactor. And I think we will talk about this cofactor a little bit more in the second half. And basically, this is another hydride donor. So what happens is that this electron pair goes from here to there, this goes here to there. The nitrogen must not have more than 5 substituents. So it delivers 1 hydride to the CC double bond, and there is a protonation necessary. This protonation indirectly comes from water via a tyrosine in many enzymes. So basically, you have a hydride addition to the beta position of this alpha-beta unsaturated compound, and you get a saturated compound in a transhydrogenation. So one proton is added from this side, and the other proton, a hydride is added from this side, and the proton is added then from the other side, which is quite a nice difference to the chemical catalyst, because a chemical catalyst would always do a cis hydrogenation. Okay. Anything? This reaction in chemistry we would call it a Michael addition. A Michael addition of a hydride to an unsaturated carbonyl function. So wonderful, we have these enzymes around, we can start working with them. Well, there is one problem, and that is these enzymes use NADH. And NADH is used also by alcohol dehydrogenases. So if you have an alcohol dehydrogenase in your reaction mixture, and you regenerate NADH, you regenerate not only the enoate reductase doing the reaction that you want to have. So for example, if you take ketoisoferone and you want to reduce it to levodopa, This is a vitamin K precursor or so. So it's quite an interesting compound. So if you want to do this CC double bond reduction, but you also regenerate all these alcohol dehydrogenases, then it's quite obvious that these alcohol dehydrogenases can reduce this carbonyl group, or this one, or in the product. Basically, in the end, what you get is explodierte Apotheke. What would be the English? You get a lot of side products. And the general strategy there is, usually people then write, oh, we wanted to explore the diversity of the different products and look at what kind of products we can make with this catalyst. But actually, they wanted to make this compound, and they only got it in roughly 10%. And there is 20% of this, 40% of the other byproduct. You have a problem. So how would you solve this? If you really want to get only the CC bond reduction. Wake up. So you want to get only the CC bond reduction, but your Aspergillus niger, your E. coli strain contains a lot of different alcohol dehydrogenases. So what do you want? What do you have to do to get rid of the carbonyl reduction?
You go to isolated enzyme reactions.
Okay, one step further. Isolated enzymes and just isolate the enzymes is not enough. You need to do. You need to purify the enzyme. I know what you meant, but you just. I wanted to hear the word purified enzyme. So of course you need to purify the enzyme, remove the alcohol dehydrogenases, and then you get rid of this reactivity. Very nice. The guys in Graz also had this idea. So they, this old yellow enzyme they used there was YQGM from Bacillus. The name doesn't really make a lot of sense. They were using this enzyme. They purified the YQGM to homogeneity, and then they wanted to apply this enzyme. So they used formate dehydrogenase as a regeneration system. And they, this is citral, citronellal as a product. And again, they saw this wide mixture of different products. What was the reason? The reason was they were using a commercial formate dehydrogenase. A commercial formate dehydrogenase usually is not a highly purified enzyme. So it is mostly a crude extract containing a whole shit of alcohol dehydrogenases. So they spent a lot of time purifying this one. And then they contaminated the reaction mixture with the alcohol dehydrogenases by putting in the formate dehydrogenase. So if you want to get rid of this keto reduction activity, either you use highly purified enzymes, which will make your enzyme preparations very, very expensive, or you try to avoid this by using bioorthogonal approaches. And there would be a lot of self-advertisement, so I'm skipping this largely. But if any one of you is interested in bioorthogonal reactions, we can talk about this. So basically, the idea is, how can we regenerate only this old yellow enzyme and keep the other enzymes inactive? And one approach for this is, we can directly regenerate these flavins by photochemistry. Flavins are yellow, so that means they absorb visible light. And if you have a molecule that has absorbed light, then you excite it. You have a photoexcited, more reactive molecule. And this more reactive molecule then can react with a co-substrate. That could be formic acid, it could be EDTA or something else. And it oxidizes this co-substrate. That means it gets the electrons from this, and we will have a shortcut into the FAD or FMNH2 without using any NAD in this system. So we can get rid of the NAD. So if we remember here in the mechanism, NADH was only used to reduce the flavin cofactor, and then it goes out. So basically what we need is, we need a system that brings 2 electrons and 2 protons into this flavin, and photochemistry is one example. There are many other approaches possible nowadays, but you can simply reduce this flavin to the reduced flavin and then use it for the reduction. And I can say that all these approaches that we've been using, the visible light approaches and things like this, where we get where we do not regenerate the nicotinamide cofactor, we never see any reduction of the keto group. And we are using crude extracts. So that's another quite simple solution. So much for the self-advertisement. I would suggest we have 5 minutes bio break, cigarette break, coffee break, unless there are any questions or comments so far. No, we need oxygen here. Thank you. So to continue with the second part, and I'm serious, this is now the really, I'm trying to move on the other side. This is the really exciting stuff. Because with monooxygenase, so you can use alcohol dehydrogenases for oxidation of alcohols. Okay, geschenkt. Not really an interesting reaction. From a chemical point of view, it's a reverse reaction of the reduction reaction. But when we talk about monooxygenases or oxygenases, we are talking about inserting oxygen into non-activated, into non-functionalized CH bonds. So for example, you can, with these enzymes, you can transform cyclohexane into cyclohexanol, which, it's a simple oxidation step, but this oxidation is terrifically difficult using chemical catalysts because oxidations are so simple. So oxidizing organic compounds is something that we do, right now, getting electricity. This is from coal. If you drive in your car, you oxidize alkanes. So oxidizing alkanes is fairly easy. But the problem is to do this oxidation in a controlled way. So to stop at a certain level. Now, if you start your engine, you directly oxidize everything to CO2, to the thermodynamic end product. That is easy. But to stop the reaction at a level, like cyclohexanol, that is the challenge. And that is a challenge that with chemical catalysts today is not so easily met. And there is one simple reason for this. So if you take cyclohexane, you have very inert CH bonds. So you need a catalyst that puts in, visually speaking, puts in energy into the CH bond, activates the CH bond so that it can be reacted with oxygen. The product of this reaction actually now has another CH bond which is more reactive than the previous CH bonds. So the product of the reaction actually can react with the catalyst much faster than the starting material. So basically, you have a chain reaction. The further oxidize your compounds, the faster they react. And then, of course, it will be difficult to stop at a certain level because you need a catalyst that is powerful enough to insert the first oxygen into the CH bond. So, but enzymes can do this. So we are in Delft, we're working with an enzyme that can hydroxylate cyclohexane into cyclohexanol. Alvaro knows quite a lot about this enzyme. And we can actually stop the reaction at cyclohexanol, or the worst byproduct is cyclohexanone. But we definitely do not burn these compounds. We selectively hydroxylate them. And there is other reactions you can do with monooxygenases, like epoxidation reactions. Okay, that is fairly easy with chemical catalysts. But you can also do halogenation reactions. So you can insert a halogen into a CH functionality. And I'm not aware of any chemical catalyst that can do this with high selectivity. And there are the so-called halogenases that actually do this with very high selectivity. Admittedly, not very efficiently right now, but I'm sure that in a few years, the halogenases would be very, very interesting and practical catalysts for selective halogenations. So with chemistry, we would have to do a radical halogenation, which in the end means we halogenate everything. With halogenases, only one halogenation and in only one position. And you can change the position by changing the enzyme active site. So you can play around with the position where the halogen is introduced. Highly exciting reactions. Well, and the reason for this is, so on the one hand, we need a highly activated catalyst, a highly activated oxygen transfer reagent. So we need a reagent that brings in oxygen into very not reactive CH bonds. And at the same time, we need to have selectivity so that the product is actually not converted any further. And this is done by enzymes. So we have these highly activated oxygen transfer catalysts, like iron 5 oxocomplexes or organic hydroperoxides, which are very reactive agents. But at the same time, these agents are embedded in an enzyme active site. So a soluble catalyst, so if you would take this catalyst and put it into solution, and you put it together with an alkane, this very reactive oxygen can react with every CH bond in the alkane. Because both are liquid, both can diffuse, so whenever this sees a CH bond, it reacts with it. In an enzyme, these very reactive agents are embedded in an enzyme active site, and the enzyme will make sure that, of all these positions that can, in principle, react, this oxygen only sees one position. So by specifically binding the substrate relative to the oxygen transfer reagent, we achieve selectivity, or enzymes achieve selectivity. That's really very exciting. So what do we need to do in order to make these reactions run? So they are oxidations, and therefore, in a way, it is not quite obvious why you need to bring in electrons if you want to do an oxidation reaction. But the reaction mechanism usually is a reductive activation of oxygen. So we have O2 from air, and the O2 then is reduced to the stage of hydrogen peroxide. And that is a reduction step. And then this hydrogen peroxide equivalent, like this one or sort of this one, they then do the oxidation reaction. So in order to do an oxidation reaction with a monooxygenase, we first need to bring in electrons. Okay, and just to summarize this, and don't take this too serious. There is no such ion as O2+. That doesn't exist. But this iron 4, iron 5 species, usually we would still call it an iron 5 oxo species. Probably it's better described as an iron 4 radical in the porphyrin ring species. But basically what you have there is you have a highly oxidized iron atom. So this iron is very hungry for electrons, so it's trying to polarize this iron oxo bond in such a way that it gets more electrons from the oxygen. So it's it tears at the electrons stronger than the electronegative oxygen, and as a result, this almost reacts as an O2+. So highly reactive ion that inserts then into a CH bond. And a little bit less reactive, but nevertheless versatile, is these organic hydroperoxides. So here, the peroxide, which is a very powerful oxidant already. Those of you who have already put their fingers into hydrogen peroxide, you know that this is very reactive. But it's even more reactive when it's bound to an organic molecule because of the electronics in there. So this oxygen actually also almost reacts as an O2+. But please keep in mind, O2+ does not exist. But it's more or less the reactivity that we would expect from an O2+. And embedded in an enzyme, so that these highly active species, these highly active oxygen transfer species, only see one position of the molecule and not all the other positions that they could react with. So we have high reactivity and selectivity, and that is only possible with enzymes nowadays. So we need electrons to do reductive activation of molecular oxygen. Usually these electrons are delivered from the nicotinamide cofactor, and if you need to regenerate the nicotinamide cofactor, use one of these systems. With all the issues, environmental, ethical issues or so, but if you want to do the reaction, screen a few of these enzymes and you will for sure find one of the enzymes that will regenerate the cofactor, will be compatible with your enzyme. You can go and run with this. Well, that's part of the story, and now comes the part where I present a hypothesis, maybe an opinion by me, and I would be happy to have a discussion with you all about this. So in principle, we just need to regenerate NADH. Then this NADH interacts with the enzyme. We get reduction of molecular oxygen. We get the reaction running. Well, that is true for some monooxygenases, but many monooxygenases actually have a more difficult molecular architecture. So the NADH does not directly deliver the electrons to the oxygenase, to the monooxygenase also, but it gives its electrons to a mediator molecule. That could be a flavin, that could be a ferredoxine, or whatever, via another enzyme, via a reductase. So the mediator is reduced, and then the reduced mediator delivers its electrons to the monooxygenase. And then this does activation of molecular oxygen and oxyfunctionalization of a substrate. So the electron transport chain, so the pathway the electrons need to take, is quite more complicated than with the alcohol dehydrogenases. With the alcohol dehydrogenases, NADH was binding to the enzyme, it was directly delivering its hydride to the substrate and then going out. So a direct interaction. Now, the NADH actually does not really interact with the oxygenase, but it interacts with the reductase and then a mediator, flavin, ferredoxine or so, interacts with the oxygenase. So from my point of view, that has two problems. On the one hand, we want to use this enzyme to do the reaction. Now, this is the cool part, but we have to use 2 other enzymes to make electrons available, and actually the nicotinamide, the nicotinamide cofactor and this mediator. So we need 4 co-catalysts in order to bring electrons into the oxygenase. That's complicated, and it's probably complicated to optimize such systems. That's one thing. And another thing is what I call the oxygen dilemma. So what happens very frequently, at least in our experiments, in our experience, is that these reduced mediators do not deliver their electrons to the oxygenase, but on their way to the oxygenase, they see molecular oxygen. And, there is a compound that has a lot of electrons, and there is molecular oxygen. So the molecular oxygen directly takes the electrons without the enzyme. So oxygen can react with the reduced mediators. You get a shortcut in the electron transport chain. So the electrons are given to oxygen and not to the oxygenase. And at the same time, you make hydrogen peroxide, which is a problem. It kills enzymes. It kills you in the end, if you are drinking too much or whatever. So we have 2 problems, complicated electron transport chain and the oxygen dilemma. There is this side reaction, and at the same time we cannot get rid of the oxygen because the oxygenase needs the oxygen as a substrate. That's a dilemma. So one example, actually a current example that we are working on, is styrene monooxygenase. And this is a typical example for this. So styrene monooxygenase does epoxidation of styrenes to the enantiomerically pure epoxides, but it gets its electrons from FADH2. Actually, FADH2 binds to the enzyme and is activated, makes this hydroperoxide, and then it catalyzes it does the epoxidation reaction. And this FADH2 is actually really diffusing from a reductase to the monooxygenase subunit, and there it can react with oxygen. And then, of course, there is a nicotinamide cofactor, and you need to regenerate everything. So we thought maybe we can make this a bit more straightforward. And our idea was to use a very simple synthetic analog of the nicotinamide cofactor. So we call it mNADH, mimetic NADH. It's not a very new idea. So these mNADHs were reported in the 50s or so already, but they have not been used very much for biocatalysis. So one thing of these mNADHs, of course, they are much cheaper because they are chemically synthesized in 2 or 3 steps. So in contrast to 800,000 euros per kilogram, we're now talking about 60 euros per kilogram. So they are much cheaper. And they actually can directly react with FAD because their chemical reactivity is different from the reactivity of the natural nicotinamide cofactors. So we can directly reduce the FAD to FADH2 and give the electrons to the styrene monooxygenase. Nice. So instead of having this, and this, we just use this compound and we can do the reaction. So we started working on the reaction, we started optimizing everything, and of course at some point you also start optimizing the FAD concentration. And what we expected was, at very low FAD concentrations, we would hardly get any FADH2, so the reaction would be slow. And that's actually what you see. Now, these here are different enzyme concentrations. But basically what you see is that the rate goes up when we increase the FAD concentration. But then at a certain point, the rate goes down again. And we had to fight with this thought, why does the rate go down again for quite some time? Now, one obvious assumption, of course, is that styrene monooxygenase is inhibited by the FAD. Well, unfortunately, STY-A does not really interact with FAD. We've done calorimetry on this, and there is no binding between the enzyme and the FAD. So it cannot be any sort of product inhibition. It took us a long time to understand what's going wrong here. And it is the oxygen dilemma. So somehow, higher concentrations of FAD accelerate the oxidation of FADH2. Yes?
So if you add catalase, do you get a higher rate at high FAD concentration?
Higher rate at higher FAD?
So with catalase, you would remove the...
Now, just a second. Catalase is necessary in order to remove the hydrogen peroxide, in order to increase the robustness of the process. But this has nothing to do with the reactivity, because, it took us. The first time I saw this problem was probably during my PhD, so around 2002 or so, and I was struggling a lot in trying to understand this. This actually is a publication from 1974. It's a review. So if I would have spent a few minutes in the library trying to look it up, I would have found these equations, and that would have explained everything. So the question is, how can this catalyze the oxidation of this one? In principle, this reacts with oxygen, and then that's it. So which role does the oxidized flavin play here? And it is quite simple, because the FADH2 does not react with molecular oxygen. That is a mistake that is done very, very frequently in the literature. For example, talking about flavin-dependent oxidases. They always say that it's the FADH2 that reacts with molecular oxygen, but FADH2 is really slow with molecular oxygen. FADH2 actually is a very stable molecule in the presence of oxygen. But what happens is that FAD and FADH2 can actually proportionize. So they interact, and they form a mixed redox state where both of them have a radical character. So they are semikinones. And this actually is a very fast reaction. So these are the rate constants of this equilibrium reaction. So that means the more FAD I put into the reaction, the more I shift this equilibrium to this side. Right? Le Chatelier shifting equilibria. So this one is stable against oxygen. It does not react with oxygen. But this one reacts with molecular oxygen almost diffusion controlled. So the moment molecular oxygen comes close to one of these semikinones, they react with each other. So you get oxidation, you get superoxides, suboxides as a byproduct, which then proportionates to hydrogen peroxide and molecular oxygen. So we do catalyze the oxidation of FADH2 by the addition of FAD. And that's what we see. The more FAD we put in, the lower the epoxidation rate, because this oxygen dilemma becomes more severe. Is that clear? So what you need to remember here is FADH2 actually is stable against molecular oxygen, but the radical of FAD, the reduced radical, that is the one that reacts very quickly with molecular oxygen. So we're on a good way to understanding the oxygen dilemma. So it needs to be a radical. And if you look a little bit closer at many monooxygenases, many of them use the flavin cofactor, and there I've shown you the oxygen dilemma. But many of them also use iron sulfur clusters, and these are one electron donors as well. So these are radicals as well. So we can assume, we have not done the experiments, but we can assume that also these will react very quickly with molecular oxygen. And now we have the oxygen dilemma for almost all monooxygenases or for many of the monooxygenases that we want to use, and particularly for the very exciting P450 monooxygenases. Okay, this, you should forget this. This is maybe only for the chemists among you. There is a reason for this. And it's actually the Pauli rule that explains the oxygen dilemma. So the rule of Pauli says the sum of spins before a chemical reaction must be the same sum of spins after the chemical reaction. So if the number of spins, of electron spins, changes, then it is a forbidden reaction. Forbidden reactions are slow. And if the sum of spins before and afterwards is the same, then this reaction is allowed and it will be fast. So if we have a normal covalent bond, then there is 2 electrons in there, one up, one down with the spin. So the sum of spins is 0. And what you need to know about molecular oxygen around here is it is triplet oxygen. So the normal oxygen in the atmosphere is actually a radical and not, usually we would draw molecular oxygen like this. So there is no radicals in there. But probably the better way to draw molecular oxygen is to draw it like this. And that means molecular oxygen has 2 spins showing up. Or showing down, that's not important, but it's the sum of spins in molecular oxygen is 1. So now we just need to do a little bit of math, and this is actually easy for me. 0 plus 1 should give 1 in the end of the product, but the product has a total spin of 0, so the number of spins changes in the reaction. If you have a radical, like flavin radicals, like ferredoxins, you have 1 spin, 2 other spins, so half plus 1 gives half a spin. And after the reaction, you have 1 half spin. So this reaction is spin allowed, so it is fast. And actually, did you ever ask yourself, why do we not burn in oxygen? There is a lot of oxygen here. And the reaction of our skin, of our body, with molecular oxygen is thermodynamically quite favorable. Why don't we burn? Because we are all composed of covalent bonds, so the total spin of our body, let's say it, is 0, and the spin of molecular oxygen is is 1. So the spin for the reaction body plus triplet oxygen is forbidden, so it's slow. So we burn quite slowly. If we would live in an atmosphere with singlet oxygen, we would burn immediately. Now, there is no reason to why we are not burning. I see some contradiction over there.
We just didn't understand what kind of oxygen?
So, the normal oxygen in the atmosphere is triplet. And body plus triplet is spin forbidden, slow. But if we would use singlet oxygen, if you make singlet oxygen and you expose your hand to singlet oxygen, then you will be burnt to the bone probably quite quickly, I would say. Yeah, so we could try to draw some MO orbital schemes, but I don't want to try this. So this is just a way to some food for thought. How can we solve the oxygen dilemma at some point? Because I do believe that this oxygen dilemma is the biggest problem that we have to face with monooxygenases. If you supply a P450 monooxygenase, for example, with a lot of electrons, but these electrons do not end up in the product, then it's quite a useless reaction. You're pumping a lot of current into the system, and the engine uses this current very inefficiently. So if you want to make a few micromolar of your product, pharmaceutical applications, that's probably fine. But if you want to go for large-scale application, then you really want to have your system 99% of the electrons floating into the system. And I believe that with the oxygen dilemma, with monooxygenases, it will be very, very, very difficult to solve this problem. But at least we need to start approaching this problem by understanding this. And I think this is something that I hardly read in the P450 literature, that electrons are wasted.
So is it a stability problem or a problem of efficiency?
I think it's a problem of efficiency. Now, in the reactions, they always pump in huge amounts of catalase. So I believe that the in situ concentration of catalase is actually not so much the problem. But in some cases, we see that 99% of the electrons go this way to hydrogen peroxide and not to the substrate. So I believe it's a problem of efficiency.
And I think we would have the same problem in photosynthesis, right?
Yes.
So how does photosynthesis solve this? Is it just it has a low efficiency, or are there mechanisms to cope with that?
I think it just lives with it. I think I'm still trying to understand, because it doesn't make any sense to me. Now, why should nature come up with such a wasteful process? And especially when we're talking about photosynthesis, but also if we're talking about end oxidation. There's also radicals involved in the end oxidation, so there must be a lot of uncoupling in the end oxidation as well. And I think I found a few articles, I still have to read them. Okay, that's another problem. But I think it's just inefficient. And the view that nature is perfect maybe is not the right view. I don't have a final answer to this. So maybe in 5 or 10 years, I will be standing here with much more self-confidence, and I will tell you, the oxygen dilemma, it was so obvious, and that no one saw it. But maybe also that someone will prove me wrong here. But at the moment, I see a lot of evidence that there is this oxygen dilemma, there is this problem, and we need to solve it if we want to use P450 monooxygenases efficiently. And I think this is not being solved so far. So we have done a few experiments. I'm not going to bother you with this, but you might actually ask the question, why? Why did nature not come up with a system where it uses the NADPH directly? Why did nature choose? Why do P450 monooxygenases use mediators in between? And there is a simple chemical reason for this, because the mechanism of a P450 monooxygenase does not take a hydride from NADH. And NADH is a hydride donor. So, but what happens with P450 monooxygenases is, first there is an iron-free, incorporated in this heme. This iron-free takes up 1 electron. Then it binds molecular oxygen. Then it takes up a 2nd electron. Then there is some rearrangement, water elimination, and we get to this iron-5, iron-4 oxo species compound 1 that does all these wonderful reactions. So we have a mechanism dictated by the iron that needs 2 successive steps of electron transport. And NADH cannot serve as as a single electron donor. It can only serve as a hydride donor. So you need to have a relay system in between. Now, if you try to incubate P450 monooxygenases with NADH, you won't see any reactivity, or very, very, very little reactivity. So the chemistry dictates this. If you want to use iron as a metal for your chemistry, you have to put in a relay system in between NADH and the iron, and the price you pay for this is the oxygen dilemma. That's at least what I believe. If you have any better idea, I will be more than happy to discuss. So, actually, I should be done now. I just would like to, so part of our research is, how can we deal with the oxygen dilemma? Can we actually solve the oxygen dilemma? And we have a few ideas of solving it, but we have no real proof at the moment, so I cannot really talk a lot about this. You can avoid the oxygen dilemma by using oxygen-independent enzymes. Anaeroid reductases, NADH, alcohol dehydrogenases. There is no oxygen involved in there, so you don't have this problem with oxygen dilemma. And what we see is that the efficiency in terms of turnover numbers and everything of these enzyme systems is usually much higher than the efficiency of the P450 monooxygenases, which again is sort of an indirect proof for the oxygen dilemma. Or you can use the oxygen dilemma, and I will take maximally 5 minutes for this. So what does use the oxygen dilemma mean? That means using so-called peroxygenases. And peroxygenases are enzymes that are very similar to P450 monooxygenases in the sense that they use the same compound 1 to do hydroxylation epoxidation reactions. But in case of the peroxygenases, hydrogen peroxide is donated to this. So we have already, these enzymes already use the reduced and activated molecular oxygen. So they don't need all this electron transport chain. They just use hydrogen peroxide directly. Until 5 years ago or so, there was one famous peroxygenase, and that was chloroperoxidase from Calderomyces fumago. That is a nice enzyme. You can do very nice sulfoxidation reactions with this, but actually it's a very inefficient enzyme with many other reactions, so that it never became very popular in organic chemistry. And actually this enzyme also is quite difficult to express. I did a calculation of the sigma price, and for a kilogram of CPO, you pay 60 million euros, 60 million euros. And very often this enzyme does a few turnovers only, so that the cost contribution of this enzyme to the final product usually is something like a few million euros per kilogram. So you will have to have a very expensive product. And for some reason, no one really looked into this, but there is actually many more peroxygenases around there in fungi. And there is a group in Zittau, and they started looking at new peroxygenases, and I think they started with the agrozyber A-Grita enzyme, which we actually got into our hands, and that is going to change the world, this enzyme. And because it's much more reactive, it's much more stable than this CPO, and this is just the beginning. So I'm not going to go through all the details of all the wonderful reactions we can do with this enzyme, but I think this is going to change the world. And actually, starting with A, going down this list, I think we can still expect a couple of new enzymes to come up that actually solve this oxygen dilemma. So we can get the same chemistry, but we only add hydrogen peroxide to this system to make the reaction run. So I think this will be the future more efficient. Yes?
When you use hydrogen peroxide in the reaction and also with monooxygenase, is that toxic?
Yes. Thank you. Next slide. So this second part now. So this is just a selection of different reactions that you can do with this enzyme. Wonderful. So basically all the P450 chemistry you can do with this agrozyber enzyme. You can do directed evolution of this agrozyber enzyme. So you can change the substrate scope. I think this is the future of oxyfunctionalization chemistry. But these enzymes are toxic. These enzymes are dying in the presence of hydrogen peroxide. I believe no one really knows what is the exact mechanism. So there is, ring cleavage is proposed, just organic radicals being formed, hydroperoxide radicals being formed. Probably the inactivation of these heme enzymes by hydrogen peroxide goes via various pathways. But what we do know is if there is too much hydrogen peroxide around, these enzymes die. You can also see it, the reddish brownish color of these enzymes disappears quite quickly because there is oxidative bleaching of these enzymes. So what you need to do in order to make these enzymes applicable, you need to provide hydrogen peroxide in the right concentration. So the concentration should be like high enough to get the enzyme running, but low enough to minimize the inactivation of this enzyme. And one popular way of doing this is to use in situ reduction of molecular oxygen. So you take oxygen, you take an enzyme that reduces oxygen, and you get hydrogen peroxide. So the oxygen dilemma. This time we are keen on this hydrogen peroxide. We don't want to avoid it. We want to make it in a controlled way. And one popular way of doing this is glucose oxidase. And you remember everything I've told about glucose dehydrogenase as a system? The same is true for this one. Now, we have 24 electrons that could be used, and only 2 electrons are used. So I think this is a problem, and we need to come up with a better way of doing this. And I just want to make a very, very long story short, self-advertisement. Actually, what you can do is you can take methanol as an electron donor. So methanol, you can oxidize it 3 times, and you get 3 hydrogen peroxide equivalents out of this. So we have a very small molecule, and we get 3 equivalents of hydrogen peroxide out of this. As compared to glucose, with glucose oxidase, you have a large molecule and you only get 2 electrons out of this. So I believe complete oxidation of methanol to carbon dioxide is going to be one of the best approaches for doing this. I could show you now another half an hour of presentation showing that we combine it, we take an alcohol oxidase, a dismutase, and in principle we take a formic acid oxidase to do all these oxidation steps. The first 2 steps work very, very nicely right now. We have big problems with the formate oxidase, and any one of you who comes across a nice formic acid oxidase, please give me a call. We will be very interested in any new formate oxidases that are available and around, because this is a limitation of this step. And I want to make a long story short. So here, this is an experiment that we did. So we took this argocyber peroxygenase, a few other enzymes in a cascade to oxidize methanol 3 times to get it into CO2 and to do an hydroxylation of ethyl benzene into phenylethanol. The world has not been waiting for this product, but for us it is a nice model product, model substrate, because it shows in anti-selectivity of the reaction, and actually it's a good substrate for the enzyme. And what we did was we took 5 millimolar of methanol, and we could actually make something like 15 millimolar of product, which actually means that we have oxidized methanol 3 times to get all the electrons out of there. There is a photochemical approach, but I don't want to talk about this at the moment. If you're interested in the photochemistry, Janis, Robert, this is quite established here. They know everything about the photochemistry. Alvaro, of course, also. So I would like to finalize this part. Oxygenases do the real cool chemistry. So insertion of molecular oxygen into non-activated CH bonds, that is really very exciting chemistry. I personally believe that the oxygen dilemma, the problem of electrons being wasted in a non-productive pathway, is going to be a big issue for the application of these enzymes. And I believe that at the moment people have been mostly looking at engineering these enzymes for substrate scope and for anti-selectivity, and no one, or not many people have been paying a lot of attention to what is happening to the electrons. And now that we are moving with these enzymes into application, we really have to answer this question: what is happening to the electrons? I believe there is a problem. But you can use the oxygen dilemma, and hopefully you can also solve the oxygen dilemma, and then we'll get also the P450 monooxygenases, very practical catalysts. So all in all, redox chemistry is cool. You can do a lot of reactions using redox enzymes that chemically are very difficult and where the selectivity with chemical catalysts is usually very poor. So biocatalysis really has a few solutions available for problems that do exist in chemistry today, and that's why this area of research is exciting. And finally, I would like to recommend you one book for reading. If you're starting with biocatalysis, I really would recommend to you the book by Kurt Faber, Biotransformations in Organic Chemistry. I think there is a new version, a new volume from 2012 or so. It's actually a cheap book. I think it's 30, 40 euros or so. So that's a very, very, very nice introduction into the field. If you want to start doing biocatalysis experiments and you don't know how to do them, have a look at the Bioorganicum. Or there is a new book series, Science of Synthesis, SOS, that gives you, recipes. Take 5 milligrams of this, 10 milligrams of this, mix it at 150 RPM or so, and then you will get the product. So here you find the recipes to do your first experiments with biocatalysis. And I really would not recommend you to buy the enzyme catalysis in organic synthesis, because that book series, it's 3 books, it costs 1,500 euros or so. It is really not a book for students to get into biocatalysis, but it is a book that every group leader should have in his or her office as a reference. But if you want to get into biocatalysis, take the Faber. So I will be very happy to answer any questions, and Thank you for your attention.